So we got a conical tank, radius of 10 feet, height of 20 feet, and mounted with its circular base horizontal and its tip pointing downwards. The oil weighs 50 pounds per cubic foot. How much work is required to pump the oil out through the top of the tank if the tank is full to a height of 16 feet? So what we want to do first is put in our axes, and we'll assume that the origin is at the bottom of the tank. That makes things easier here. So this will be my X. There we go. Okay, so this is my Y. Let's see, we know this tank is 20 feet tall, so we might as well put a 20 there. And then let's see, we've got thickness on this thing is our delta Y sub I. Our height of it, well, let's see, what are we doing? I guess we still, no matter what, we're going to need the height in here. So we'll put that over here, Y sub I, and put our locations for that. Arrows, okay. And let's see, in this case, we're pumping the oil out through the top, so we are going to need our displacement to go up here. So maybe I'll just put that in there. Let's see, was that 20 minus Y sub I? Okay, there's my displacement. Okay, and now we need to think about what we've been putting together every time for these. So delta F sub I is our weight of the ith disk of oil. Is this oil? Yeah. Okay, so that's going to equal, in this case, the density is 50 pounds per cubic foot. Okay, we're multiplying that by the volume. Well, let's see, that's going to be pi r squared. What's the radius going to be here? Looks like it's x sub I, right? It varies as you move that up and down through this tank. And so we're going to have to make it our x coordinate there. So pi x sub I squared times our thickness, height of the disk, right? So that's our delta Y sub I, and this will be in cubic feet. Okay, now we need to get that x sub I in terms of Y sub I. So here we're going to look at the cross section just like we did for the circular tank. Remember how we used the circle? It was the cross section of the circular tank to figure out the relationship between the radius, which was x sub I there, and the y coordinate. We're going to do the same thing here. Really what we've got in this case is our cross section is a line. It's really, I guess, two lines, but we care about the one on the right here. So let's see if I can get it lined up about right. So that would be my line, extended a little bit. What is the equation of this line? You know what this point is right here? What are the coordinates of this point?
10,
Yeah, 10, 20. That helps us here, right, to determine what the slope of this line is. It goes to the origin, it goes to the point 10, 20. What's the slope? Rise over run. 2. Okay, so the equation of this line is going to be y equals 2x. So that is what's going to go over here in place of, well, not quite. We've got to use that to come up with what we need, right? So from that, we can write that x sub I is equal to y sub I over 2, right? So that's the expression that we're going to replace x sub I with over here on the right. So rewriting this, simplifying a little bit, we've got 50 pi. X sub I is going to be replaced with y sub I over 2 squared delta y sub I, and the cubic feet cancel. We end up with pounds, which makes sense. Okay, my pie is a little bit messy, but other than that, looking good. Okay, now we're going to write our expression for delta W sub I. The work done in pumping the ith disk out of the tank, right? So work to pump ith disk out top of tank. All right, so let's see, that's going to equal the weight of that disk, which we have just above there, 50 pi y sub I squared over 4 delta y sub I pounds times the displacement that we've written over there of 20 minus y sub I feet. Okay, so I suppose we could simplify that a little bit. We've got 50 over 4, so that really could be written as maybe 25 over 2 pi y sub I squared times 20 minus y sub I. We'll insert that there. Delta y sub I, and then the units, we're left with our foot-pounds. Okay, so keeping those units in there really makes this clear, makes it easy to see what we're coming up with. Really, these aren't hard because they make sense if you work through them like this. Okay, from that we can then write our integral. I guess if I'd left space, I could have put my constant out front, but didn't do that. Okay, let's see, we've got y sub I, so we could actually multiply that in. We're going to get 20y squared minus y cubed dy. Okay, and the limits of integration here, let's see. Are we pumping the whole thing out or just part of it? Okay, we're pumping it through the top of the tank. The tank is only filled to a height of 16 feet. So we're going to be integrating from 0 to 16. Mm-hmm. Okay, so we've got it set up. I suppose I'll just tell you what this equals because it's not too hard to do the integration steps. We end up with exactly 409,600 over 3 pi foot-pounds, or approximately 428,932 foot-pounds. Okay, so that gives us a sense to be able to compare when you do a couple of these different ways what you're getting. All right, so far? So the water tank is in the shape of a cylinder, has a radius of 10 feet and a height of 20 feet. Well, our first step is going to be to add in axes. So we're going to put at the bottom of the tank the origin, and then I guess the x-axis is going to come out through the sides this way. Okay, and so that's going to be our x-axis. The y-axis is going to come straight out the top through the middle there. I guess it maybe should have been making it dotted inside, right? Because that's all inside the tank there, but I didn't. But you could make it dotted if that helps you. Okay, the top of the tank is at what height here? 20 feet. So we know that's 20. I'll put a feet mark on there. Okay, and now we need to draw in a representative disk of fluid here. So coming around it, back behind it, and then give it some thickness. Okay, this is going to be our disk of fluid. Okay, we'll make it have thickness delta y sub I. Its height is going to be y sub I. And then its displacement, the distance we have to actually put the liquid in, is through the bottom this time, right? So its displacement happens to be how much? How far? If this disk of fluid is at a height of y sub I feet, how far do you have to move that disk of fluid from the bottom up? Y sub I feet. Yeah, so we actually already have the displacement there. It's equal to the height this time. All right, so let's see what we're going to have then. The delta F sub I, the weight of the ith disk of fluid. And this is water this time. Yep. All right, that's equal to the density, which we're told here is 62.4 pounds per cubic foot, times the volume of this disk, which in this case, what is the radius of each disk? 10 feet. Okay, this happens to be at 10 here. It's constant, so that's cool. Pi r squared, so pi times 10 squared. the area of the base, times the thickness, delta y sub I, and that's going to be in cubic feet. So this time we don't need to have a formula to convert the x to y. Most of the other time we will. Okay, so let's see. This is going to simplify to 100 pi, so 6240 pi. Units are going to be actually delta y sub I is still there too. Units are going to simplify to pounds. Okay, then we're ready to go for our work done to move the ith disk of water into place. Okay, that's going to be equal to the weight of that ith disk, so 6240 pi, delta y sub I pounds, times the displacement. We just said that's going to be just y sub I feet this time. Okay, gives us an expression for that. It's going to be easy enough to work with. Foot-pounds for our units. Okay, we're ready then to integrate. So the actual work done. Let's see, is this tank full or is it going to be full? No, it wants to know how much work is done to fill it to a level of 15 feet. So what will be our limits of integration here for y? 0 to 15, that's correct. All right, so 0 to 15. And then our 6240 pi, we could have put out front if we'd had the forethought. And then it's just y dy. So let's see, that's going to be integrating 3120 pi y squared, evaluated from 0 to 15. So 3120 pi times 225 minus 0. Okay, what is that going to give us? Let's see. 702,000 pi foot-pounds. Okay, or approximately, what is that? 2,205,398 foot-pounds. Okay, so this is how the pumping problems work. We basically have to just keep looking at the various shaped tanks and how we represent the slices and the radii or whatever's needed to make those calculations of volume times density to get the weight. That's the hardest part of the problem. Other than that, as long as you remember to write the pieces here, so the weight of the ith disk and then the work done to move that ith disk of fluid either out of the tank or into position, you're good to go. Okay, now let's go ahead and do the metric one. This is the one at the bottom on the back here. So a conical oil tank with a radius 10 meters, height 20 meters, same stuff, right? Except for meters, not feet. Is mounted with a circular base horizontal and its tip pointing downwards. The oil weighs 833 kilograms per cubic meter. How much work is required to pump the oil out through the top of the tank? It would have been nice if I'd done it to go in through the bottom, right? Because anyway, the only difference then is instead of the 20 minus y sub I, you'll have y sub I being your displacement, right, in through the bottom. Shorter distance, usually, if nothing's full anyways. All right, let's see. So, by the way, if it were a full tank, which would require more work? Pumping it out the top or pumping in the bottom when it's a conical tank like this? If it were a full tank, which would require more work? Pumping out the top or pumping in the bottom? In the bottom. Why? Yep, more oil at the top, and it would have further to travel. More of the oil would have further to travel going from the bottom to the top than it would pumping out the top. Most of it's at the top, so that goes out easy. Not as much distance, shorter displacement. Anyway, good thing to think about because it helps you get some intuition for what we're talking about here. All right, so let's see. This one. Delta F sub I, the weight of the ith disk. This helps maybe here to think about this. The weight is really the force needed to move the ith disk. Okay, but it is the weight, it's the F equals ma, though. We got to think of it that way, right? It's in newtons, not in kilograms. So here we're going to have to figure this out by the mass density that was given. It's not a weight density this time. So 833 kilograms per cubic meter multiplied by the volume. So I guess helps if we could put the rest of the stuff on here. There's my x, my y, got 20 there. Let's see, this is going to be our y sub I, and our 20 minus y sub I. This is all looking the same. Okay, and we've got our delta y sub I, all that good stuff. Okay, and then the radius is still x sub I. So that's still going to be looking the same right now. So you got your pi x sub I squared, delta y sub I. This is going to be in cubic meters. Now that's going to give us, so far, density times volume is going to give us our mass, right? So you're going to get your kilograms out of this. So then we're going to have to, in order to get the force, the newtons, we're going to have to multiply this by the gravity constant, right? So that's our acceleration. So this is the only time we have to do this, though, when we do it with metric. We don't have to do this with the English units because they happen to already give us force units, pounds. So here we end up having to multiply then by 9.8 meters per second squared. Okay, giving us kilogram meters per second squared, or newtons, which is what we're going to be getting out of this. So this part here, that gives us the mass. And then we're multiplying here by the acceleration. Okay, they give us the force altogether. All right, so let's see. That ends up giving us 9.8 times 833. I think that ends up being 8163.4. Okay, bring pi along for the ride here. We know what x sub I is, so we can put that in here. Y sub I over 2 happens to be the same relationship here. Squared delta y sub I. And this then is our kilograms meters per second squared, or newtons. Okay, so now our delta w sub I, our work done. We get this piece right here, our force, 8163.4 pi y sub I squared over 4 delta y sub I newtons times our displacement of 20 minus y sub I meters. And from that, we're going to get Newton meters. Okay, and rather than writing this over again, why don't we just go right now to our work. We're going to be integrating here. Let's see, what did it say? 16 meters again, similar, different units, right? So same limits. We've got our constant. We could have brought it up front, but keep forgetting to do that. 4 pi, and we've got our y. Could we multiply that? We can multiply that in right now if we want to. So let's see, that's going to be 20. They put the over 4 out here, so we'll do that later. Let's see, that's going to be 20 y squared minus y cubed dy. Okay, and I again won't go through the whole process here of integrating. We'll get the approximate here, 70,030,889. And the units on this are going to be effectively Newton meters, right? Which simplify to joules. Now you could just put Newton meters and be okay. All right, I'm all right with Newton meters. Just don't put joules when it's foot-pounds. You'll lose points for sure. Okay? Make sure you're consistent with your problem. Okay, so any questions on that? So now I've covered all the examples I have that I guess need to cover right now. We could always go back and do one more cylinder if we needed to, but for pumping and for work. So you've seen it. You can now do the problems that are in the book. I do recommend you still do those kind of problems, right, in the book. You might even want to use those to review for the test.